In 88 through 96, we're asked to solve for x. In 88, if the log of a equals the log of b, then a is equal to b, so we can basically undo the logarithms on both sides, provided that they are the same base. So 1 minus 3x is equal to x minus 19. Adding 3x and adding 19 to both sides, we get 4x is equal to 20, so x is equal to 5. In this type of equation, because of the domain of a logarithmic function, it's important to check your answer. And if we check, we see that the log of 1 minus 3 times 5, question mark, is that equal to the log of 5 minus 19? And we get the log of negative 14. Is that equal to the log of negative 14? Since we can't take the log of a negative number, then these two sides of the equation are not equal because they are not numbers, which means that 5 is an extraneous solution, and that means that there is no solution. In 89, we can condense this side of the equation into a single logarithm. So log base 6 of 5 times x is equal to negative 1. From here we can put it in exponential form. 6 to the negative 1 is equal to 5x. And so that's 1/6 equal to 5 times x. If you want to clear the fractions, multiply both sides by 6 and then divide, and we get x is equal to 1/30. And if we check that, when we put x back into the equation, we are taking the log of a positive number, so that's within the domain, so that solution is valid. In 90, we have two logs that are equal to each other with the same base, so we can undo the logs on both sides. 3 minus x is equal to x squared minus 8x plus 13. And if we add x and subtract 3, we get 0 is equal to x squared minus 7x plus 10. That's going to factor into x minus 5 times x minus 2. So x is either equal to 5 or x is equal to 2. If we check our results, if we replace x with 5, that's going to give us the log of 3 minus 5, which is the log of a negative number. That solution will be extraneous. And if we check with x equals 2, on the left side we're going to get log of 3 minus 2, which is log of 1. That's equal to 0. On the right side we'll also get log of 1, so x equals 2 is a valid solution. In 91 we have an exponential equation. We need to express all these powers as the same base, so I'm going to re-express all as base 2. So 8 is 2 to the third power, and 4 is 2 to the second power. And when we raise a power to a power, we multiply the exponents. So this is 2 to the 3x, and the 2 squared raised to the x plus 7 is 2 to the 2x plus 14. On the left side, we can combine these. When we multiply like bases together, we keep the base and add the exponents. So that's 2 to the 4x minus 4 equals 2 to the 2x plus 14. Now that both sides are expressed as powers of the same base, we can equate the exponents. Subtract 2 from both sides, add 4 to both sides, and divide, and x is equal to 9. It's not necessary to check every single solution on an exponential equation because exponents can be any value. They can be negative, positive, or 0. In 92, we can re-express both sides as powers of 3. So 3 to the x squared divided by 3 to the 2. And on the right side, 1 divided by 3 to the x is the same as 3 to the negative x. On the left side, when we divide like bases, we subtract their exponents and keep the base. So 3 to the x squared minus 2 is equal to 3 to the negative x power. Now that both sides are powers of the same base, we can equate the exponents. Move all terms to the same side of the equation and factor. And that's going to give us two solutions That'll give us -2 and +1. Again, in an exponential equation, no need to check because the solutions can be negative, positive, or 0. In 93, there are two approaches. One is to multiply both sides by log of x and then use a property. I'm going to use another approach here, and that is to recognize that two logs divided could be re-expressed using the change of base formula. So this is log base x of 4x minus 3 is equal to 2. Rewriting that in exponential form, the base x raised to the exponent 2 is equal to 4x minus 3. And so subtracting 4x and adding 3 to both sides and then factoring, we're going to get two solutions, x equals 1 or x equals 3. X equals 3 is a valid solution because it gives us the log of positive numbers in both cases in the logs. But however, 1, although it gives us the log of a positive number, gives us a denominator that's equal to log of 1, which is 0. So that's going to be an extraneous solution, whereas 3 is valid. In 94, we can condense the two logarithms. The natural log of x plus the natural log of 2 is equal to the natural log of 2 times x, and that's equal to the natural log of 10. Now that we have logs with the same base on both sides, we can undo the logs and divide, and we get a solution x equals 5. That doesn't make the argument of any logarithm a negative number when we check, so that's a valid solution. In 95, we're going to use some properties of logarithms to re-express 1/2 times the natural log of x. That is the natural log of x to the 1/2. And then we can further condense these logarithms. The natural log of one thing plus the natural log of another thing is equal to the natural log of their product. And so the product is 9 times x to the 1/2. Now x to the 1/2 is also the square root of x. So 9 times the square root of x. And on the other side, we've got natural log of 4. Since we have logs with the same base on both sides, we can undo the logarithms, and 9 times the square root of x is equal to 4. And if we square both sides, that's going to give us 81 times x is equal to 16, dividing x is equal to 16/81. Checking, that doesn't give us any logs of negative numbers, so we are good on that one. That's a valid solution. In number 96, we need to use a property here that 2 times the log of x is equal to the log of x squared, and that's equal to the log of 20 minus x. And since there are logs with the same base on both sides, we can undo the logarithms. That's a single log, by the way. We have to condense if there are multiple logs. And then let's add x and subtract 20 from both sides, factor, and that will give us two solutions. It's going to give us x equals -5 or x is equal to +4. The -5 is going to give us in the original equation here 2 times the log of -5, which is the log of a negative number. That's not valid because it's not defined. And on the right side, it would have given us log of 25, which is valid. So we'd have an undefined number equal to a defined number. And x equals 4, however, will give us logs of positives on both sides, so it's a valid solution.